Chapter 6 extra practice, a few extra problems for us to work through here. I encourage you work through these on your own. See if you can do this without the video's help. If you can't, that's okay. Just make sure we're getting the right practice we need and try to push yourself a little bit. Try to challenge yourself. See if you can work these on your own, and then the answers just come behind you. If you're working them right, then that's a good sign of success. If you're not, then it tells you just need a little more practice. That's okay. All right. And if you can't, again, no problem either. Just something to think about. We're given this scenario: newborn baby lengths follow a bell-shaped curve that is centered at 20 inches, the variance of 4 inches, a problem you should be able to work without the use of a calculator, so our math should be relatively simple. Find the probability that a newborn baby has a length greater than 24 inches. Again, anytime we see find the probability, go ahead and write out the probability statement. The probability x is greater than 24. And because we have a bell-shaped curve that tells us that we're following a normal distribution, and that means we're going to want to standardize our x. And as we've talked about previously, when you take an x that is normal and you standardize it, standard plus normal is a z. And so we standardize this problem. We are centered at 20 inches. That tells us that the mean is 20. Variance of 4 inches tells us the standard deviation is square root of 4, which is 2. And so that's where we get the numbers to plug in here. On the left side, I use symbols. On the right side, I use numbers. Just keep like with like. Within that probability statement, that is the probability that z is greater than 2. 24 minus 20 is 4. 4 divided by 2 gets you to 2. And then this is a greater than probability, so we want to work that into a less than probability because of the way our z table works. And then you should be able to go to the table, look for the outside value of 2.00, right? 2.0 in the column, and then the 0.00 of the columns, not a 0.01, 0.0 whatever, because we're 2.00, so look for that first value is 0.9772, subtract that from 1. And I hope you're seeing here why it's important to keep things this equals this equals this or whatever, just to make sure you don't lose things like your 1 minus, so you don't do that when you should, or so you don't do it when you shouldn't, and don't not do it when you should, right? Just help keep all that straight. Find the probability that a newborn baby has a length of 24 inches. Of is a form of is. In math, that means equal to, so we want to find the probability that x equals 24. That is an interesting question if you have a discrete distribution. Given that we have a continuous distribution, we know that the probability that we land on any number exactly is 0. We don't need to do any math. We don't need to standardize. We don't need to go to a table. We know that no baby is ever born at exactly 24 inches. You say, I was 24 inches. No, you weren't. You might have been 23.9999524, right? Or 24.0018, whatever, but no one's ever exactly on 24 inches. We may just lack the tools to measure that precise, but no one ever lands exactly on a number in a continuous distribution. Find the probability that a newborn baby has a length between 20 and 24 inches. It's just like the first one now. We just have to standardize an extra time. We've already done the standardization for the 24 part. Just need to do the standardization for the 20 parts, which is pretty simple because that numerator gets us to 0. 0 divided by anything is 0. Now be careful here, as we talked about before, when we split this up now, you have probability x is less than 2 minus probability, z is less than 2 minus probability z less than or equal to 0. This is not 0. It's a probability involving 0. So you just have to be careful of it. It's not going to be this answer. And you're not just going to say, look this value up and then subtract 0. Boom, we're done. Subtracting from 0 doesn't do anything. We have to look the 0 up as well. So again, remember, I need to drill into your brain. I need to make sure you understand that there's a number inside of a probability statement, and that is completely different than what the probability itself, the whole thing is. This whole piece gets replaced with 0.5 because the area to the left of 0 in the standard normal distribution is 0.5. So this is our original answer of that 0.9772 when we looked 2 up in the table. Previously, we subtracted from 1. Now we're going to subtract 0.5 from that to get our answer. Okay. Find the median of newborn baby lengths. Now, again, on the first 3 problems, the question is find the probability of. So I started off with, okay, probability statement, capital P, open up my parentheses. This question does not say that. It says find the median. We need to be able to differentiate between find the probability of something means write a probability statement and find some cutoff. Now notice I didn't use the word cutoff. Notice I didn't use the word percentile. Notice I didn't use the word quartile. but I used a word that relates to all of those in median. Median is the cutoff that cuts off the top half from the bottom half. It is the 50th percentile. It is the second quartile, right? So I need to make sure we're thinking through all of those words and how they can be used interchangeably. The median length is the z-score that separates the top half from the bottom half. And so I would go inside the table to find 0.5. That leads me to a z-score of 0. This one you might not have needed the table for, because you know if we're separating the top half from the bottom half, that's a z of 0. And then the question is, well, what is the x for that? Well, we can unstandardize that. You may have already got here. It's actually just the mean of 20 inches, which we've covered previously, right? That the mean and the median of a normal distribution are the same thing. And the last one, if we see a newborn baby whose length is at the 96th percentile, what is the baby's length? Similar concept to the previous problem, but now we actually are going to have to go to the table to figure out what is the z-score that is an area to the left of 0.96. Because percentiles are to the left, that is nice and simple. We just get to look up this number. If I had said I want 96% of babies to be bigger than this baby, then I would have to look up 0.04. But that's the only way to word that, where you have to subtract that from 1, is where you want something bigger than that. If you want something less than that, you're good. Or if it's a percentile, because percentiles are defined that way, we're good. We just look up that number on the inside of the table. Again, talked a lot about inside versus outside. Make sure you're straight on that and you're confident with, when I see that 0.96, I know I'm going inside, not outside. You're not going inside because it's less than 1. There are z-scores that are less than 1. You're going inside because it represents a probability or an area. Those are synonymous words, and we find probabilities on the inside of the z-table and the z-scores are on the outside. That's what we have to make sure we know. The z-score closest to that is 1.75. This is about as tricky as the decimal multiplication can get. 1.75 times 2 is 3.5. Then you should be able to add that to 20 easily to get you to 23.5 inches. And then to wrap us up here, just some concepts just to make sure that we're all on the same page here before moving on into different material. This is a good place to kind of check and make sure that we're kind of remembering all of these basic concepts. All data is either qualitative or quantitative. You can not be neither, and you cannot be both, right? You are either data. If you're neither, you're not data, right? All data is either going to be words or numbers that are used for labeling, or it is numbers that we can actually do math with, right? Quantitative data is the latter, qualitative the former. All quantitative data is broken down into either discrete or continuous, right? If you are a number, that number either has gaps or it doesn't. Cannot be neither, cannot be both. Some discrete data is binomial. So when we see a situation that is binomial, we know that is discrete. When we see discrete data, it might be binomial, it might not be. And similarly, some continuous data is normal. When we see a normal data set, we know that is continuous, but not necessarily the other way around. So make sure we're thinking through that right there. Anytime you see a normal setup, all of the rules of continuous data apply to it, maybe not the other way around. The z-distribution is also called the standard normal distribution. Make sure you know those are synonymous, right? We standardize something, we call that a z-score, but when you put standard and normal, that is the z-distribution. It's a specific case of the normal distribution, right? It's a type of the normal distribution. There's one z-distribution. The mean is 0 and the standard deviation is 1. The center is 0, the spread is 1. Binomial data is identified via the requirements listed in section 4.3. There are a lot of them. I'm not listing them here. Remember those 4 criteria. And normal data is identified via the use of words like normal, bell-shaped, or via a plot showing such a distribution. There's no checklist to go through like there is for binomial. It's just you're going to see one of those words, normal or bell-shaped, or I'll give you a plot, and you'll see a nice, pretty bell-shaped picture. And then to kind of wrap some of that up as we talked about here, I've gone through all data is either qualitative or quantitative. Quantitative data is split between discrete and continuous. Within discrete, there are different types of distributions. We've talked about the binomial here. There are other ones. Just want to make sure you're aware of them. We're not talking about the Poisson distribution in this course. but there are other ones as well. And then continuous distribution, there are other types of continuous distributions besides the normal. The normal is a big one that we talk about a lot. We'll talk about the t later. That is a subset of the normal. And the z also a subset, but notice I've given it a dot because there is only one z distribution. So it's just a dot. The z is one of the types of normal distributions. There are an infinite number of normal distributions that we can talk about. And once you standardize those, they all fit right into that little dot right there.